Başlayabiliriz hocam.
Good morning to you all. Today's session in the morning has started. In this session, we have two invited speakers. One of them is Ahmed Mohammed, and the other invited speaker is from University of Bradford, Professor Tahir Khan. And we will start with Ahmed Mohammed, he's an associate professor in the School of Materials and Mineral Resources Engineering from the University of Science, Malaysia. He has many publications on solvents and soldering processes. His talk is about application and characterization of tin 0.3 silver, 0.5 copper to copper solder joints by microwave hybrid heating. If our guest is ready, we can invite him to do his presentation.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, everyone, can you hear me?
Yes.
Hocam, mikrofonu yaklaşır mısın?
We can hear you.
All right. Okay, Assalamualaikum and very good morning, everyone. Okay, now Malaysia is afternoon, 2 o'clock in the afternoon. Okay, first I would like to thank the chairman today, and then to all my friends in Turkey, Professor Edenko, okay, for invitation, and then maybe we have Dr. Ali Kozel, Mr. Paira, and so on. Right. For today's presentation, let me share my presentation first. Where to share? Okay, share screen. Sorry, I'm not familiar with this PowerPoint. Okay, guys, can you see my PowerPoint?
Yes, we can see.
In the full mode, right?
Looks fine.
Okay, nice. Okay, for today's presentation, we share about the application and characterization of SNAG CU, or we just call this one SAC 305 copper solder, right? On the copper solder joint. In this case, for the today's presentation, I will discuss in detail about our new techniques for the joining, which is we using the microwave as the hybrid heating. Normally, we are using the what you call that, the oven and so on. That one was the classic one, right? So, but for today, I will share with you about one of the techniques, which is microwave hybrid heating. Okay, this is my outline presentation today. There will be first starting with the introduction, the literature review, and then I will discuss a little bit about the challenging that we are facing about this microwave heating, and then I will discuss with you with my latest result, right? My latest result about this microwave fittings, and then I just share about the methodology, result discussion, and at the end, I will summarize the finding. Okay, let me introduce to you about the solder joint. If you are familiar with the solder, it was started by the SNPB, right? Let me show you here. Okay, let's go. So it was started with the SNPB, okay? And now, due to the PB here, it's a toxic material. Now we are moving to the lead-free, meaning that without the lead. Lead is the PB. And then there are a few material that can be used for this replacement. For example, the most successful alloy is SAC, or maybe we can just use SMCU, right? SAC refer to the tin, SN, AG, and T is for the copper. And then most of the research around the world are focused on this one, SAC. Okay, and then the best is SAC 305. 305 refer to the composition. Okay, and normally for the industry, they use the wave and reflow for the soldering, right? We call this one as a reflow because we try to match it again. Maybe the original form is in the pellet, in the paste, or in the thin wire, right? So we need to reflow again, or in other words, it's to reheat again the solder and apply to the another specific application later on. Okay, the reflow, it can be by oven. Okay, and then the oven, they have the infrared, or maybe you can use the forced air convection, or even we can use the vapor phase. So there is another way that we can use to do the reflow. For example, there are a few papers reported that we can use the microwave hybrid heatings. I will share to you after this. I will discuss in detail about why they call this one as a hybrid heating MHS for the solder reflow, right? And then we hope that, and it is sure that this technique is the green manufacturing system. And then, as you know, our devices like handphone, many other electronics start to be smaller and smaller every day. So hopefully by introducing this microwave heating hybrid, we can propose the technique for the miniaturization of the components, right? Okay, this one a little bit about the process for the soldering. If I start here for the materials, okay. So after we do the material selection, and then we need to go to the process. Okay, the process can be the reflow and so on, right? After that, we need to discuss about the design, right? The design of the material, of the application. Okay, after we finish the joint and so on, then we need to go for the quality and reliability checking. Okay, if they pass here, then we can go for the specific equipment. For example, we join with the capacitors, we join for resistor and so on. That one is for the electronic. Okay, but at the end of the day, the most important thing is the cost. We cannot sell the devices with very high price just because of the material of the processing, right? So just make sure that the cost is very low. And luckily, I think that this microwave hybrid heating is one of the cheapest and the fastest way to do the reflow, right? So there is the big hope, okay, big opportunity for us to go to the microwave heating, microwave hybrid heatings, okay? Okay, I will share a little bit about the process for the solder interconnect reliabilities, right? Similar to previous slide, then starting from the materials, right? We go for the solder alloy and paste. We need to know the component types and then the size of the materials. and then component termination and geometry of material as well. Okay, after we finish this one, we go to the design, right? So design is based on the, for example, PCB board layout and the components. Like sometimes they have many components, sometimes they just a few components. And then on the board, on the PC board, they have different type of the component. It can be the pad, it can be the hole, and so on. After we finish that one, we go for the housings, right? Either the housing will affect the joining or not, right? Housing and mechanical structures. Okay, after finish all these things, we go for the manufacturing. Normally in the factory, they will use the solder paste deposition. Okay, and then component placement, and then they use the flood. Flood is used to avoid the initial oxidation during the reflow. There are many ways that we can reduce this flood. The type of the flood, it can leave it there or we can clean afterward, right? It's a very big topic if you want to talk about the flood, right? Okay, soldering profile, they have the atmosphere, the wave dynamic, and process for the reflow. Okay, so at the end of the day, we need to go back to the target, the objective, which is the application. So when we talk about application, they have the thermal, mechanical. This one is involved the moving and the heat maybe generate during the application of the materials, right? Okay, and then dynamic mechanical properties. We can use for dynamic mechanical properties, and then sometimes our application facing the corrosion. That's why they put here electrochemicals and electrical applications. Okay, everything can move forward here and goes to the reliabilities. But in this case, I just want to discuss detail about the solder joint reliabilities, because this one is very important, because we can do many joint, we can do different type of joint, but either it's a reliability, they have some reliability or not, or maybe they have a problem with the reliabilities. Okay. Okay, just let me show you about the basic about the solder joint fabrication. If you want to do the basic joint fabrication, we just take that the solder, put it on the copper mat, copper plate, and then we do the heatings. Okay, and depends on times. Okay, for example, if the time is enough, they start to melt, and if the time is more than enough, it tends to be melted, right? This one we call as the wetting property, right? So these are the example, the very basic joint fabrication. So the joint here, actually the joint word here refer to the joint between the copper substrate in the bottoms to the solders. Okay, and the thing is used to join, or the joint is we consider as the glue, right? The glue is the IMC. So formation of IMC. IMC here refer to the intermetallic compound. Okay, if you can see here, the fluctuate or the wave here is actually the IMC. So intermetallic compound. This intermetallic compound is very important. Sometimes we have a very thin and it's not enough to glue the two different materials, the solder or the copper substrate. But if the IMC is too thick and it's tend to be brittle, right, and easy to detach from the copper substrate, and it's not good. Okay, for the lab testing, normally we are using these two types of the testing. It can be the butt joint, and then it can be the lap joint, right? So we can have two different substrates. For example, copper substrate, and then this is the solders, and this copper substrate, and the middle here is the copper. Okay, if you want to go details, you can follow certain ASTM. So this is the ASTM for the sampling, right? The dot bone shape. We can study the bulk of material alone, meaning that the whole material here is the solders, and then we can do the tensile. Or we can just want to study this small amount of the solders, meaning that we need to join copper to another copper and the solder in the middle. Right. When we do the join here, it doesn't mean that all the solder here can turn to be IMC. Some of them are the interface turn to be IMC, and some of them still to the SAC305. Right. Depend on application that on, or depend on the size of the material that you want to join in, right? Okay, but sometimes they also have many report. It's not just this type of or the shape of the sample that we can do. We can have the rod. We can do the rod, and then we can put the solder here, and then we can do the testings, right? So there's depend on your application later on. It doesn't mean that we need to follow all the ASTM, because at the end of the day, everything will refer back to the application, right? Okay, another one is the lap joint. The lap joints, this example, the lap joint between this surface to this surface, and then we can see that this kind of the IMC. When we do this lap joint, it's very good for us to study the IMC, because the areas that interface to the solders and then the copper are very big, and then we can see that the morphology. If you want to study the morphology, then we can see that the fracture behavior, right? It's a very good for us if you want to study the surface behavior after the failures. Then we can do that. You need to do that lap joint type of the joining. Okay, again, at the end of the day, everything depends on the application. For example, this one is depend on the, I think they use for the resistor, right? And then this is the solders joint, right? So this one we can see that it's not good because it's based on excessive solder. You see that the extra solder here is not good for the joining. Maybe this one we create the short circuit to another component, right? And then this one is so many excess solder, they call as very poor wetting, and you see that this is the component and it is the solder. It's something like the solder is not well stick to the surface of materials for the both interconnect materials, interconnect components. Okay, another one is after we're doing the soldering, and then we can see the gap, the lifted pad. So this one is not good because this one will disturb our connection later on. Okay, so these are the example that the joinings, right? That we are very, very important for us before we can do the certain application. Okay, when we talk about the solder joint fabrication, for example, we can do this very simple one, right? I think some of you are very familiar with this simple joining, right? You just use the heater here, and then there's the solders, and then it's the plug, and you can join this one into the electrical circuit. Okay, and then it flashback to my my memories that when I started doing this solder joint, I don't have the specific oven, I don't have good equipment. I just use the hot plate for the joining. I just put a sample here and do the heatings, and then we can get the joining. But the problem is the temperature here is cannot be controlled. Sometimes the heat very fast and the cooling is very long, right? And then sooner or later, I got a few grant. Then we bought this kind of the oven. So this is very good oven because we can control the reflow, temperatures, and time. So we just put the sample here and close. I don't know if you can see the knot. My sample here is very small, right? Compared to the big devices here. Okay, and then I also had the opportunity to go to the industry, the company in Malaysia. Actually, they have this kind of the oven. It's very, very big ovens, and if you can open something like this. So our component PC board, we passing through this oven. So this is the heaters. The heater can be the heat filament, they can be the infrared and so on. Okay, so this component we call as the surface mount technology SMT PCB assembly, and this one is inside the manufacturing process. Okay, I would like to bring you to another type of the method to do the fabrication. So this one is the microwave, by a microwave. Actually, if we have a budget, I would like to buy this lab type, okay, lab type microwave, because this one we can control the time, we can control the temperatures and so on. These are the very best microwave if you want to do the level 3 microwave. But unfortunately, this one is very expensive, guys. So we just move on, because the research, you need to be very creative. If you cannot do this one, then we need to find other ways. And the best one, we just use the home cooking microwave. Okay, but we need to do the temperature calibration and so on. In other ways, certain microwave, they have different modes. Mode here refer to the powers, right? Power that we apply to the system. Okay, they have the low, they have the medium, and they have the high mode. Normally, this very low is not enough to melt our solder. Then my research, my student will do the research mostly on this medium and high only. Right, so we focus to know that either the medium or the high mode is good or not. Okay, so you can do this research in the Turkey, because for sure you have many home cooking like this. But please don't do this one at home, because this tend to be a spark and then start to be a cloud. The white cloud is sometimes very dangerous. When my student doing this research, they just switch on and run away from the device, because sometimes they produce the spark. It's quite dangerous sometimes, but it's nothing. Okay, and there's no of my students died doing this experiment. Okay, let me explain to you about the what you call that, the mechanisms, right? The mechanism, if you want to compare with the conventional heating to the microwave heating. Conventional heating here is referred to the oven, right? So for the oven, the heat can come from many different areas, right? To the samples, and then sample we melt, right? And then for the microwave, it tends to be many ways, right? The heating can come from the microwave to the samples, and then this one is not enough, because if you just depend on the from the microwave, the heating is not enough. Means that we need to use another component. This one we call as the subsystem. And now we discuss later on about the subsystem. Right. Let me go back to this one. Why we need to change that from the conventional to the microwave? One of the reasons is this one need a very long time for the reheatings and cooling. But if you move to the microwave, it's a very short time. Maybe in the second we can get the that preferred temperature for the reflow, right? But they still have some drawback. For example, we need to do the calibration for the surface heating, and then it requires subsystem. You cannot just put a sample and do the heating. No, we need to use the subsystem for efficient heating. I will explain this one for the next slide. And then they have the microwave reflection, because we are dealing with the metal. They have some spark inside the microwave, right? Okay, let me explain to you what is the subsystem. Okay, so subsystem is useful for initial heating due to the ability to absorb the electromagnetic energy and then convert to the heat, right? So it is used to mainly keep the temperature of the sample to be uniform, right? We don't want that fluctuate temperature. If we're not using the subsystem, the temperature will be fluctuate, high and low. It's not good for the reflow process. Okay, and at the end of the day, it provides the initial heating of the sample before it can start coupling with the microwave. Okay, there are not many papers talking about the success story. Only a few, less than 10 papers published about this kind of matters. Okay, and okay, before that, let me show you that this is the success story, right? This is the samples, and then inside here is the box, installation box, and then this is the sample, copper substrate, and then the solders. If you can see that the particle here is our successor. Okay, so this successor we have to give extra energy to the reflow process. Without this successor, then there will be no enough energy or enough temperature to do the remelt. Okay, so this is our microwave, and this one is if they use the silicon powder, and this is the silicon carbide powders, and it is samples, right? So to the best of our knowledge, there are only this kind of the material that was used for the successor. They use the iron powders, and then also a report for the graphite powders, and then they have this silicon carbide powders. And for my words, I will discuss later on, we use the silicon wafer. You know that silicon wafer for the semiconductor research and so on. We use that one because it's a very good material to absorb the energy. Okay, this one is about the mechanism of microwave heating, hybrid heating. And then I will focus about the silicon wafer that we use for my research, right? This is a silicon wafer. I think you know better than me, right? For those from the physics departments, right? We are using this one for the semiconductor research and fabrication of semiconductor devices. So I just use this one and put it here, right? And these are my samples, the solders on the samples on the copper substrate, and this one is the successor. But because the temperature is very high, it can break the glass from the microwave here, right? Normally they provide the glass, so we just put the ceramic pad here. I'm sorry that this arrow should be referred to this white ceramic pad, right? So when we do the heatings by the microwave heating hybrids, it's starting by supply the microwave to the sample, and this one is the spark produced from the sample because we are dealing with the metals, right? And then the yellow one here is the heat energy. They will disperse, okay, disseminated on the materials. But as I said before, this one is not enough to make the samples. That's why we need to put the silicon wafer at the bottom of the sample. So this one is the silicon wafer. This one is the ceramic pad, silicon wafers, copper plate, and the solder. This one is our sample, right? This one is our sample. Okay, by combine two heating systems directly from the microwave, and then the heating actually starting from the directly from the microwave, but they start to heat the silicon wafers, and then the heat from the silicon wafer move again to the sample. Means that we have two types of the heating, directly and from the successor. And for sure, this one is more than enough to do the reflow. And combination of this type of this heating, that's why we call this one as the hybrid heatings. Okay. Okay, so these are the challenges when we do this kind of research, means that dealing with the microwave, and then the increase in the reflow time simulate the growth of IMC. We don't know that how fast or how thick the IMC will form. And then sometimes the non-uniform heating by conventional reflow that can be overcome or not. The high power consumption by the reflow, hopefully we can cover by this microwave. And then some complexity of experimental design by powders, such as if you can see that my previous slide that they are using the silicon carbide powder, iron powder, but in this case we are using the wafer. Wafer is the what you call that, the plate, easy to use compared to the powder. We don't want that this powder will contaminate our sample and so on. If you use the silicon wafer, it's just nice at the bottom of the sample, so there will be no direct contact to them. And then there, for sure, there are limited research on the microwave operation for the joining, so this open a very good opportunity for us to do the detailed research on this. Right. Do I still have time? Because I just in the middle of the presentation. The chairman is okay?
We have around 6 minutes.
Okay, so let me know if you want to stop me, right? Okay, so the objective of the this current work is to fabricate and optimize parameter for the reflow, as you see by microwave heating, and then one of the most important is to know the IMC behavior, the group, and then the effect of this microwave to the tensile properties. Okay, this is my our methodology, simple methodology. We are using a copper plate with the 1 mm thickness, and then this one is 9.9 purities, and we use the ACC paste. So this one is commercial. You can buy this one online, alpha solder paste. Okay, and then we want to compare the property of the solder by oven fabrication and by microwave fabrications. So we will try to compare to this one. Okay, for the microwave, we can only just set at 250 C and hold for the 60 seconds. And this one is the setting is based on my previous student, and they produce very good properties. Okay, and for the microwave heating, we need to find, or we need to do different type of various type of the parameter, and then at the end we will conclude that which one is the best. And for your information, we are using this coding H40, means that the H here refers to the high mode, and the 40 is the time, 40 seconds. It's just second, right? And then the subsystem we use the silicon wafer P type. Okay, this one is silicon wafer and some sample on it. Okay, and then we run for wettabilities, SRD, SCM, E-test, tensile, and so on. Okay, this one is the solder mounting for the checking for the wetting and so on, right? So this is the solder paste. So we can see the paste here. And then this is the way we do the tensile, because we just want to get a very nice small sample on the copper substrate. Okay, so this one is before reflow, and then we put inside the microwave. So this is ceramics, these are silicon wafers, and this is our sample. And then we run for the reflow. So there are two-way heating here, as I explained to you before, directly to the samples, and then the heat from the substrate, silicon wafers. And at the end of the day, so this is our solders. You can see that they start to melt and form the bumps, something like this. Okay, and then for the tensile, right? For the tensile properties, we do the butt joint. So we just made a very small gap here, and they put a sample. If you can see here, we need to put another copper here, because we just need to make sure it's the fit to that gap. And then at the end of the day, we can just remove this as one component, and we can have very nice final finishing. And we take this one, run for the tensile. This one is as reflow, and this one before tensile. Actually, sometimes it's not very nice. We can get not very nice joining. So what we can do, we just need to polish the surface, right? Polish the surface, and then run for the tensile. Okay, before we can do any at the testing, we need to do the temperature calibration because we are using the home type microwave. Then we don't know what is the best temperature or what is the highest temperature we can get. So we can take the thermocouples, right? This is the thermocouples, and then we put inside here. So this is the joint thermocouples, the sample, silicon wafer, and we run for the microwave to our specific parameters. Okay, and for your information, we run for the AC. We found that normally the reflow temperature is about 220, right? Something like that. Okay, so this is the reflow. Then we hope that even we are using the microwave oven, we hope that we can get this, we can reach these temperatures. Okay, this is an example when we do testings. Sometimes we are using the low mode and there will be no wetting at all. But if you are using the high mode at very longer time, it tends to be overheating. It's something like burns, right? On the surface. So these are not good, right? And then normally, this one for the microwave, we need to adjust or we need to find what is the accurate time and mode. And finally, yes, we can get a very nice wetting, and it's comparable to the oven. So, okay, so means that this microwave can be used to the joinings. Okay, so when we run for this one is the result from the ovens, right? The highest is 250. We need to go a little bit higher than a normal temperature than this one because to make sure that everything melt before we can stop the run here, right? And then we try to compare. This one is for the microwave, for the medium mode, and then for the high mode. So we compare both of them. So if we use the high mode, we can get or we can reach about this 250. Meaning that this amount or this setting, for example, at high and 40-second of microwave, they can reach this temperature. Means that this is a very good setting for the reflow. Okay, if you are using lower than that, for example, medium, and then we cannot even touch 200s before it start to do the cooling. So some of them are not good, right? So we found that one of the best is H40. H meaning that high mode, and then 40 seconds. Okay, we also want to try to know that what if we heat the sample with or without subsector, with or without the silicon wafer. If we are using the silicon wafer, we can have very nice temperature curve. But without the subsector, they tend to be fluctuate. I think you know that how the microwave function, right? When the microwave run for at least 1 to 2 seconds, they start to stop, and then heat again, stop. That is the reason, and that is the problem. If you are using without the subsector, we need to use the subsector to maintain the temperature, and hopefully it can reach to this amount. But this one is run for the medium. Not if it can touch, but it's not a very short time, right? Okay, we also run for high mode. Okay, for the 40-second, with or without the subsector, and you can see that it can pass 250. So we consider that this setting is one of the best setting for the next for the joinings, and then for the next categorizations. Okay, sorry, I need to take a water first. Okay, sorry. Okay, and then we go for the wettability testings, and then okay, so this one for the wettability analysis, I try to go faster as possible, right? When we run for the wettability, we found that for the H mode, it can give us a very better wettability from here compared to this medium, right? And when we check for the wetting angles, and they produce a very nice wettability compared to others, right? Sorry, I need to go faster because I'm taking very long time, I think. Okay, this one for the structural analysis. When we run for the SRD, one of the problem is the amount of the solder here is very small, very limited. We just cut and run for the SRD, the pit normally dominated by the copper plate. So that is the reason you need to cut the rest of the area with just the sample and the copper behind it. So it's tend to be very small here. Okay, and then later on, that's why then later on when we run for the SRD, we can get very nice, or we can get to see the important peaks. For example, the important peak for the for this one is copper 6, Ag3SN, and for sure they have a lot of beta SN, right? So when we run for the this one for the mediums, and then for the high mode, we can get very nice what you call that peak for this IMC. Means that when we have the IMC, then we can have the joint, right? Okay, this one is the morphology analysis, comparison between the medium mode to the high mode. Right, for the high mode, we can see that here, very big area, very big grain compared to the medium, right? And then at the same time, we can see that the white powder here, the white powder here actually refer to the AgSN, right? And then when we run for the different time, for sure, starting with a very thin IMC layer here, and it tend to be very thick at the end of the picture here, because when we compare to the 100-second to 40-second, for sure this is a longer time, and then they will form this IMC copper 3SN. Okay, something very interesting about this microwave heating, we can get the copper 3. Normally, when we run for the conventional, it's very difficult to get copper 3 because it's involved temperature and time. But in this case, for the microwave, we can get very thin copper 3. So what is the copper 3? So this one is the enlarged pictures. Normally, when we run for the reflow, we can get copper 6 SN. Copper 6 SN can be at the interface and inside the bulk of the solders, right? And this enough for the joinings. And then at the same time, sometimes we can have Ag3SN, the which is powder here. Okay. But when we run for this microwave, luckily we can see that they have another thin small layer. Maybe we can see this one, guys. All right, we can see this one. The number 3 here, this line, is actually the copper 3SN, copper 3SM, and copper 6SN. Normally, when we run for reflow, they will start to form copper 6SN 5. But if you have enough time and temperature, sooner or later they will form another one. It's good to have this layer, but sometimes for the thick layer is not good for the mechanical properties, because this one will be the cause of the failures, right? Okay, and then I do have very good students run for this experiment. She done a very nice job to calculate the thickness of each layers. So these are the thickness of those layers, right, for the IMC, right? This one is for the medium and then for the high mode. And for sure, guys, when we run for the longer time, high power, and for sure we can get very thick IMC compared to the lower power and so on, right? Okay. Yes. Okay, let me go faster here. Okay, and then we run for the tensile, and then we found that the high mode can give us higher tensile property compared to the medium mode, and this is the result. And we can also study the properties here, right? Let me go. Okay, and then the difference between the schematic view, the IMC growth for the medium and the height is presented by this one. For the medium, they start to form a vertical IMC, but for the high mode, they turn to be horizontal. This is the bigger and fluctuate. This is very good for this word. Okay, again, we study for aging, and then for sure aging, we can produce copper C and copper 3. Okay, and then this one is the surface and cross-section morphology for the aging. She started with the microwave, and then we do the aging inside the oven. We cannot do the aging inside microwave because it will take very longer time. If we run for the longer time, sometimes it's very dangerous. I don't know, maybe something like that. Okay, and then we run for the longer time, then we can see that the differences in the grain size and then formation the white powder here. White powder refer to the AG3. Okay, and then we have some opportunity to do this color index, and then we can see that for the longer time, the AG3 accent tend to be very big here and so on. Okay. Okay, and then this one is the IMC growth. Sorry, I need to go. Let me go directly to the tensile. Right. The comparison between the microwave and conventional one. Right. For sure, because we had a very thick IMC, then it can give us a very higher. You can see here, right? It can reach about 50 compared to the conventional is about 30 megapascal. Right, means that is a very good tensile properties. And we do the compare here, and then as explained here, because this one is based on the IMC thickness. I've tried my best to explain this one by using this schematic drawing. The failure of the fractures, this one is the fracture, it can be two different modes. It can be from the bulk of the SEC, or maybe from the interface between the solders and the IMC. But another one is the failure of IMC itself. But in my words, in our words, that normally are related to the mode number 1 and number 2. Sometimes it's very difficult to see the failure. If you can see here, this is the failure, example of the failure on the tensile. Okay. And then we can see that the ductile and the shear from the samples. Okay, if you can go to very detailed ones, something like this. Okay, so this is the end of my conclusions. I tried to presentation, try to do conclusion. Okay, we are able successfully to fabricate the solder reflow by microwave, microwave hybrid heatings, and then the acceptable range on the wetting angle and spreading area, optimized microwave parameter observed, and the best is H40. And then the IMC grain structure thickness is reliable and comparable to the conventional one, even better, right? And then the tensile butt joined by MHF reflow show a great better than conventional. Okay, at the end, I would like to thank to my student Mariana Sad for his excellent work, and then I also would like to thank my sponsor Malaysia Team Board, the government. Okay. So that's all my presentation. Sorry, taking very long time, the presentation. If you have any question,
If you have any questions, we'll be very happy to. Yes, Professor.
Did you try adding any kind of copper nanoparticles?
Just a question on his soldering material. The material obviously was a traditional copper tin. Has he ever tried adding copper nanoparticles as a part of the soldering material?
okay, that's very good question. This field we consider as the composite solders. Okay, there are many reports said that these nanomaterials can improve the mechanical properties. But on our side, we found that the problem with the nanoparticles, because the density of the nanoparticle is lower than the density of the metal, as I said, they tend to go to the outside of the solder itself, meaning that on the surface is not to be part of the IMC. That is the thing that we can explore more, or to find the best nanoparticle that can be embedded or closest to the IMC itself. Thank you.
Thank you. Thank you, Professor. Is there any more questions?
I have a question.
Yes, Dr. Nazri, Dr. Vedal.
What is the prospect of doing microwave heating on reflowing composite solder using, maybe we use a ceramic filler within the solder? Is it may cause any floating of the filler?
Yes. Okay, Dr. Piras, it's a very good question, because when we are dealing with the composite materials, the filler itself tend to be moved out from the solders, and the reason is because the time taken is very long, and then they have time to go outside, move outside to the solder. But if you are using the microwave, hopefully it can overcome, because microwave in the very short time, for example, just 40 seconds, we can get the reflow. And then with this 40 seconds, hopefully the nanomaterial will stick inside the solder, and something like we not allow them to go outside the solder itself. Hopefully, we will do detail later on. This one is very good research if you can explore. And I always ask my counterpart from the Turkey, come and join us. It's a very good opportunity. Thank you, Dr. Firdaus.
Thank you. Thank you, Desmond.
Thank you very much for the question. If there is any more questions, there is. Thank you very much for Professor Azim.
Thank you.
It was a nice talk, and it was very informative. I wish we could give you more time, but unfortunately, we don't have much time at the moment. Thanks again. Our next guest, next speaker is Professor Tahir Khan. He is obtained his PhD from Cambridge University. At the moment, he is holding a position of 15th Anniversary Chair at Cambridge University. He is also President of Abbottabad University of Pakistan since 2019. And his expertise lie mostly in the direction of diffusion bonding and TIP bonding of ferrous and non-ferrous alloys, and he also works on nanomaterials. I invite him to the stage. He's already on the stage, and we are listening to the professor. We are trying to adjust the screen at the moment. Yeah. Okay, Professor, stage is yours.
Okay, I just want to open up the.
O değil miydi?
So it shows full slide. It's in Turkish, so I don't know which one to
Hmm?
press the tab. So it's full screen.
Bilgisayarda sıkıntı olabilir mi?
Yok.
Hocam ikisi bağlı zaten. Birini alıyoruz, birini alıyoruz.
Bu şimdi buna bağlı. Şuna
Tamam. Şükrü hocam ekranda ne görünüyor? Ekranda gelen şey.
Masa üstü.
Görünüyor tamam.
Sinyal. Sabah çalışıyordu sonra. Hangi? Bu mu? Şu bağlantı kablosu. Prize bak, prize. Geldi.
Yes. Assalamu alaikum and good morning, everyone. One of the worst things that you can do is give a professor the stage to talk about his research. He will never finish. So, so today I will certainly just spend about 25, 30 minutes, not more than that. So let me just test the computer here just to see if the next slide will move. Okay. Good. And how do you do that? Okay, thank you, Sukru, for giving me a very nice introduction. I'm currently Vice Chancellor at Abbottabad University of Science and Technology in Pakistan. So the research that I'm presenting is a snippet of different things that I've done with my PhD and research fellows. So this research is a culmination of different types of things that we've been doing. And it focuses on nanoparticle enhanced bonding. So the professor from Malaysia said that you know, the nanoparticles are less dense, and what we theoretically understand is that these particles are lost from the joint region. But until you actually do the experiment, you find some interesting results, and that's not exactly what happens all the time. So the work that I've been working on for a long time now is looking at dissimilar materials,
So aluminium joining to titanium, titanium joining to steel, steel joining to magnesium. So this is where the interest is. And as most of us know who are working in the fabrication and manufacturing industry, we know that we want to combine different materials together. And so this table gives us an idea of the different reasons to why we want to join different materials. So at the top there, you have function, mechanical requirements, quality, machinability, and at the bottom you have some of those other less direct reasons to why we want to put different materials together. And these applications are very strong in places like the aerospace, automotive, and certainly electronics industries. Now, being a professor, we are always working with limited funding. And so what you see here is a homemade diffusion bonding machine. And this was made when I was a lecturer starting to teach at Brunel University in West London. So this machine was fabricated at that time, and this has lasted me my career. This piece of equipment went with me from London to Canada, and it was with me for 14 years in Canada. And now this equipment is back with me in the University of Bradford as well. And some of my students are still using this equipment. So, but it served me very good purposes. Now, some of you may know about diffusion bonding very well, and some of you may know a little bit about diffusion bonding. But the TLP, transient liquid phase bonding, is a slight variation of diffusion bonding in that we use an interlayer. So what we see is several steps that are used in the bonding mechanism. So we start off with a solid interlayer, and this interlayer will melt. Either it's the melting point of the interlayer, or it's the eutectic point that forms between the interlayer and the base metal. And then if we hold at the bonding temperature for a certain length of time, diffusion mechanisms will encourage isothermal solidification. And normally there is a last step process which we call homogenization, and this usually involves some kind of grain growth across the joint, or at least a uniformity in diffusion processes in that joint region. So when we are working with dissimilar materials, we have lots of challenges, and the differences in both mechanical and physical properties are those challenges. So this is a example of those types of challenges. So here we see that we are joining using copper interlayer, pure copper, and at the top we have a austenitic stainless, and at the bottom we have a magnesium alloy. So when you are looking at the bonding of different materials, we can expect interesting results. And so this micrograph shows you a lot of white patches. So these patches here are intermetallic compounds. So whenever we have dissimilar materials, we can expect to see these. So we are trying to reduce these intermetallics or try to control them so that we can have good joint formation, but also somehow change the shape or the volume of these intermetallics. And so what we find is that as we increase the bonding time, sometimes the isothermal solidification process tends to collect these intermetallics. So when the joint is forming, it first melts, and then when it solidifies, it goes in the reverse direction. So the intermetallics then move towards the joint interface. And this is what we tend to see in the last picture here. So some of this control and how we can do it is a big problem for us. This is another example. Again, we have a 316 stainless steel and we're using a nickel interlayer. Nickel and magnesium form a eutectic, and therefore we can expect some of the same problems again. So the intermetallics are again forming, and as you heat and hold for a length of bonding time, these intermetallics tend to increase. And why is it a problem? Well, this is the problem. The hardness within the joint region increases, and that creates a problem because we will have a point of fracture. This is a stress concentration point. Now, diffusion bonding and transient liquid phase bonding processes have been around for a very long time, for 30, 40 years. But these problems have to be solved, and very few researchers have solved these problems. Another example is if you try to use TLP, transient liquid phase bonding, to join a composite material, aluminium composite. Now, aluminium composite is a great material, fantastic properties, but we cannot use it in a proper way. We cannot use adhesives or rivets. And how can we maximize the use of the strengthening particles? So if we use transient liquid phase bonding, this is what happens. We get a region of reinforcement that forms at the joint. So this is the original interface, and the interlayer melts, and then when it solidifies, it pushes the particles. And again, this is a non-uniformity in mechanical properties. So although this process and diffusion bonding have been around for a long time, very few people have focused on the problems of this method of joining. So I've listed some of the problems. Dissolution of parent metal. Dissolution results in a change in the strengthening of the particles and the strengthening of the joint. Bonding time can control the isothermal solidification process, and that can control intermetallic formation, but intermetallics do not disappear. And then homogenization, which is the last step in the joining process, unfortunately can cause grain growth. And grain growth then means you have a weaker bulk material. So how can we try to change this? How can we try to solve some of this? Well, some, including my team, we've looked at seeing what can happen with the interlayer thickness. Because when we use different interlayer thicknesses, we can control the volume of liquid formed at the joint. Reducing bonding time. If we reduce the bonding time, we can control the volume of intermetallics forming. But if you reduce the bonding time, then we may get a weak joint because the liquid does not flow between the joint interfaces. Select appropriate interlayer composition. This is something that we've also looked at. And then the final one is, can we use nanoparticles? Can we use nanostructured interlayers? So some of the techniques that potentially can solve these problems now are going to be discussed. So for example, interlayer thickness. So if we look at some of these reactions here in these micrographs, we start with a 20 micron coating thickness, and this is 10 microns. Immediately inside, if you look at the volume of liquid formed, with this liquid formed, the width of the volume, it's much less for the same bonding time. And the amount of intermetallics is also less. So the thickness can have some control. And if we reduce the interlayer thickness to 2 microns, the intermetallics, the large ones, have partially disappeared. So this is a bond between magnesium and titanium. So interlayer thickness has some ability to control things. Parent metal meltback is when the width of the joint begins to increase in size. This width is controlled by the diffusion of interlayer material out from the joint into the bulk material. So if we look at the different diffusivity coefficients of the different materials that we have, then you can control the isothermal solidification rate and also control the amount of particle non-uniformity. So this is a micrograph that shows us what happens if we use a copper tin, very much a soldered joint, and we look at what happens at the different bonding times. So I showed you a micrograph of all the particles close to the joint. So here, when we use a mixture of copper and tin, and then we increase the bonding time, we get some interesting results. So the tin has a very low diffusivity in aluminium. So the tin now does not go out. What happens is isothermal solidification is controlled now by elements coming into the joint, and that causes the solidification process. So here we see for a longer bonding time that there is particle uniformity within the joint, and the particles are still present in the joint region. There is no segregation of these particles. And this, as I say, is explained by the diffusivity of the different elements away from the joint and into the joint. So what we've done is taken away control of isothermal solidification by diffusion away, but given control the diffusion into the joint. And if we look at the hardness profile, now we do not get a very high hardness in the middle, but a undulation in hardness values. And this is shown in the joint strengths as well. So right in the initial stages, if we look at the shear strength of the joint region, then for 2 minutes, it's the lowest. But if you look at the longer bonding times, we can actually regain that strength as well. So again, this is now another example of what happens if we try to control the bonding solidification process by using a dispersion of alumina. Alumina being a ceramic dispersion. So what we see is that for very thin coatings, 15 micron nickel coatings, we form a eutectic between aluminium and nickel. And for 1 minute, we can see that the joint region has formed. And interestingly, the particles are not lost from the joint. The particles are still present here inside the joint region. We would expect the particles, like the professor in Malaysia said, the particles are less dense, they would be lost from the joint region. But this is something interesting. And what we find is that with these particles, if you have a thicker coating, 15 microns, we have the segregation effect. But if we control with the thickness of the interlayer, then the particle dispersion is less destructive within the joint region. So we can combine both the combination of nanoparticles to strengthen the joint and also control the thickness of the interlayer that we are using. And this is what you see here. So in the beginnings, you see a very high peak in the middle for all of them. Here, we see a peak, but it begins to decrease, and the width increases as well. So there is a more uniformity as we reduce the thickness, but also have presence of particles. So the alumina particles will give the higher hardness in the joint region. These coatings are produced by electrodeposition, and the process is sometimes known as electrophoresis because these particles become trapped with the nickel atoms and they move to the substrate surface together. So the coating itself has a very fine grain structure. So this is a higher resolution imaging of those particles, and you can see the nickel grains here, and the dark dots are the alumina ceramic particles. And this is a better micrograph here of the two combinations. The light regions being the nickel grains and the darker regions being the ceramic particles. And again, here on a high resolution SEM scanning electron microscope, you can also see some of these particles present in the middle, and our analysis shows you the presence of your alumina with a very high aluminium peak. Here what we find is that we've also got the detection of alumina present within the joint region. So we were able to detect both the nickel alumina. Further away in the different reactions, we find different nickel aluminide intermetallics forming. So you can use these particles and they do have an effect. And as the bonding time increases, the hardness begins to decrease as well. And what we find is that the shear strength as a function of time is also better for these joints. And this is a better comparison for pure copper. You can repeat it for copper or nickel. We did it both for copper, alumina reinforcements as well. So for just pure nickel, we got a value, pure nickel here, and for our alumina, nickel alumina dispersed coatings, we get better strength. The particle size also is important. Obviously, here, this color histogram shows you what happens with pure nickel, but with a 50 nanometer, the finer the particles, the strength is a bit better. If you use 500 nanometers, the strength is a little bit less. So these particles are present. Some of the interesting things that we found is that as the nanoparticles are present within the joint region, what we find is that the liquid formed is less. So if we use pure nickel, a big region of the joint melts, but if we add nickel with nickel alumina, the joint region is much less. And this is shown here in these two examples. So the thickness of the eutectic is much less. And this is an example with copper nanoparticles. And this again is another micrograph showing what happens if we use a mixture of copper and nickel nanoparticles. So not a coating, not a solid interlayer, but a mixture of copper nickel particles. So the measurements of the eutectic widths are shown in this diagram. So joint zone width, showing the eutectic width as a function of the nano coating type. So the lowest type of eutectic width formed is for our mixtures, nickel, copper, and copper nanoparticles. And this is proven in the shear strength values as well. So shear strength is a function of the type of coating we use is shown here. So the nickel coating, pure nickel coating, is just here. And then what we find is that we get the best strength with a copper nano, nickel, copper. Here, nickel copper combination gives us the lowest strength. And that was because we got the lowest eutectic width forming. So mixing the nickel and copper nanoparticles speeds up the joining process. So why does it speed up the joining process? Okay, that's the next slide. This is just a fracture surface showing you where the fracture occurs. But this is an interesting result. When we make the nickel composite joints, copper nickel joints with our bulk materials, and we put it in a TGA, thermogravimetric analyzer, what we find is that the curves for pure copper and copper alumina have shifted. What we find is that the melting temperature for the copper, nickel, or copper alumina nanoparticles has shifted to a lower temperature. So the temperature, in fact, the melting begins not to occur at the normal eutectic, which may be 540, but it occurs at 500 or at 510. So this shift in our eutectic temperature means that the solidification process starts much faster. And this is why we think that we get a change in our eutectic width and a change in the strength. So just in summary then, so dissolution and meltback can be reduced using and controlling the thickness of the interlayer. Second, the nanoparticles can be used to reduce the eutectic liquid thickness and thereby increase solidification. The nanoparticles present in the interlayer can provide a greater joint strength than if we use just a pure metal eutectic forming interlayer. And the size of these nanoparticles affect the dispersion process and the extent of strengthening that we see within the joint. So the different people who have contributed to this work are listed here in this final slide. So Kavian Cook was a PhD student of mine and then became a research fellow. Dr. Anas is now a PhD. He completed his PhD. Dr. Abdulaziz Al-Hazza now is also.
Can you send me the WhatsApp?
University.
Kalau boleh, if better, you can send me the picture of the sample itself. And then I will find my staff that are expert on that thing. No worry, no worry. All right, send me the message. All right, thanks. No worries. Okay, bye.
Very nice presentation. If you have any questions, we're very happy to see.
So thank you for your presentation. Firstly,
in this project, distribution of disperser is important here. If it is important, how can you control homogeneous dispersion contribution in matrix space? Thank you.
Right, if I understand your question is, can we use this process to change the dispersion in a bulk material?
In this project, homogeneity of dispersion is important.
Yes.
How can you control homogeneous distribution of disperser?
Within the joint?
Yeah.
By two methods. One, the composition of the interlayer. Secondly, controlling the eutectic width. The eutectic width, if it is big, the dispersion is non-uniform at the joint. Okay, and by controlling the solidification process and the diffusion of elements, you can reduce the eutectic width. So two processes. The interlayer thickness affects the eutectic width, and the composition affects the eutectic width. Thank you.
Is there any more questions? I'll ask one question. Might be to see. One of them is our guest was asking about how can you control the distribution of these reinforcing particles, but you said composition, change of composition might help. Do you think any other external forces or external effects might affect the distribution, like ultrasound or vibration? Will it help with the thickness of the controlling of the thickness of this eutectic zone? Is there any prospect of it?
Yeah, it's a good question, Sukru. The ultrasound or ultrasonic types of welding processes have been used to try to control dispersion within the liquid phase. However, the problem here is that the joint widths that form are very small, and the process of solidification is quite rapid. It initiates within a few seconds, as soon as the joining, as soon as the diffusion processes occur. So you're looking at widths, maximum width of the liquid forming are about 50, 60 microns. So applying the ultrasonic method there within a few seconds has not been so great.
Why do you see fast solidification? Is it because of the volume of amount, or is that metallurgical effect?
It's a physical effect because of the diffusion of elements into the joint. So if you're thinking about the bonding process, as you heat, there's diffusion beginning to occur immediately. And then when the critical level of elements A and B mix, then you form the eutectic. And already you have a lot of diffusion of elements from the bulk material into the joint region. So as soon as you form the eutectic and then move, I didn't show the mechanism, but as soon as you hit the solidification boundary on your phase diagram, it will start to solidify.
Even though the temperature is high enough for.
That's right. That's right.
Thank you. Thank you. Thank you. Thank you very much for your presentation.
Hocam katılımdan
Katılım belgesi. Katılım belgesi yok mu hocam?
Katılım belgesi verdiniz ya. Hadi hocam.
Size böyle.
Hayır, ben öğrencisiyim. Siz verirseniz daha iyi olur. Finish our next speaker's presentations. The next speaker is
Türkçe hocam. Türkçe mi? Türkçe hocam.
şimdi sıradaki araştırmacımız Cihan Yakıpoğlu. Kendisi Akres Otomotiv'de kaynak yönetim uzmanı. Tercümanlığı mühendisliği mezun olduktan sonra imalat mühendisliğinde Sakarya Uygulamalı Bilimler Üniversitesi İmalat Mühendisliği yüksek lisans yapmış. Burada ufak bir değişiklik var. Sunacağı makalenin başlığı değişmiş. Sunacağı makalenin başlığı Effect of Shading Gas in Splashes and Mechanical Properties in Collision Boxes Combined by Cold Metal Transfer Methods. Hepsini dinliyoruz. Buyurun.
İlk olarak herkese merhaba. Kısaca ben de kendimi tanıtmak isterim. Cihan Yakıpoğlu, 3 yaşındayım. Ekoloji malzeme mühendisliği lisans, imalat mühendisliği yüksek lisans, aynı zamanda işletmende yüksek lisans mezunu. Yaklaşık 8 yıldır bir işletmeyim. Son 3 yıldır rahat ve sokakta kaynak üretim uzmanı olarak çalışmaktayım. Biz bugün burada okul arkadaşımla beraber toplandık.
Sorabilirim. Metalurji Malzeme Mühendisliği mezunsun değil mi? Nereden mezunsun?
Bartın Üniversitesi.
Bartın Üniversitesi.
Teşekkür ederim. Bugün burada okul arkadaşımızla beraber üretim haklarımızda yaptığımız toplam 4 tane denemenin sunumlarını yapıyor olacağız. buradaki kendi üretim hakkımızdaki gazaltı kaynak proseslerinde yaptığımız çalışmalar olacak. Hatlarımızda gazaltı kaynağını 32 robotta, robotik sistemde kullanmaktayız. Buna başlamak gerekirse soğuk metal transfer yöntemiyle birleştirilen çarpışma kutularında koruyucu gazın sıçrantı ve mekanik özelliklerine etkisini sunuyor olacağım. Toplamda bir 10 dakikamızı alacağım. Özet olarak biz bu çalışmada otomotiv sektöründe çarpışma sonucuları istenen parçaların üretiminde kullanılan galvaniz kaplı 2 milim kalınlığındaki SCGA 400'lü çift fazlı çelikleri birleştirdik. Birleştirme işlemi soğuk metal transfer yöntemi kullanılarak yapılmıştır. 2 milim kalınlığındaki galvaniz kaplı SCGA 400'lü çeliği CNT birleştirme yöntemiyle MB205 diye adlandırdığımız %93 argon, %2 oksijen, %5 karbondioksit oranlarında oluşan bir gaz karışımıyla %100 karbondioksit koruyucu gazın aralarındaki farkları SG2 çelik özelliklerin sıçrayarak alınanla birleştirilmesi sonucunda çıkan sıçrantı miktarları, mekanik özellikler, iç yapı özelliklerini inceledik. Bildiğimiz üzere otomotiv endüstrisinde son yıllarda yakıt ekonomisi ve daha iyi performans için araçların ağırlıklarını azaltma çabaları oldukça yüksektir. Binek araçların ağırlığı ile birlikte yakıt tüketimini azaltıp araçların güvenliğini arttırmayı sağlamak için yüksek mukavemetli, kolay şekilde alabilen çelikler kullanılmasına özen gösterir. Gelişmiş yüksek mukavemetli çelikler otomotiv endüstrisi tarafından yüksek mukavemetleri ve kolay şekilde alabildiği nedeniyle tercih edilmektedir. SCGA galvaniz kaplı çelikler otomobilde çarpışma sönümleyicilerde, yan panellerde, aks bağlantı parçalarında ve güçlendirme parçaları gibi çarpışmaya maruz kalan kısımlarda kullanılmaktadır. SCGA nedir? Soğuk haddelenmiş, galvaniz bağlanmış çift fazla çeliklerdir. Düşük ağırlığa sahip olmalarına rağmen yüksek dayanımlara sahip oldukları için önem kazanmaktadır. Bu çeliklerde yumuşak ferrit maddesinin sünekliği verirken ferrit maddesi içerisindeki sert matenzit yapıda mukavemeti vermektedir. Bir nevi DP400 doğal fazla çeliklerin benzer özelliklerine sahiptir. Bizim yaptığımız bu yöntemde birleştirme CNT gold metal transfer yöntemi TURKUAZ firması tarafından geliştirilen soğuk metal transfer olarak adlandırılan mikmak prosesidir. Bu yöntemdeki amaç düşük ısı girdisi, distorsiyonları engellemek, sıçrantıyı azaltmaktır. Bu teknik nasıl çalışır? Bu teknik proses kontrolünde en önemli noktası telin hareketidir. Birinci harekette ark periyodu sırasında dolgu metali kaynak havuzuna doğru hareket eder. İkinci pozisyonda dolgu metali ark havuzuna daldığında ark söner, kaynak akımı düşürülür. Üçüncü harekette kısa devre arasındaki geriye doğru hareketi damlacık kopmasına yardımcı olur. Kısa devre akımı düşük tutur. Son harekette de tel hareketi tersine çevrilir ve süreç bu cycle'da devam eder. Burada da gördüğümüz üzere sistemin telin hareketi ve damlacık transferlerini bu şekilde oluşturmaktadır. Deneysel çalışmalarımızda SCGA çeliği 400'lük kullanılmıştır. Bu çelik saç 2 milim kalınlığında ve yüzeylerde 45-60 gram milimetre galvaniz kaplıdır. Bağlantı elemanı olarak SG2 çelik seçilmiştir. Koruyucu gaz olarak da PB205 ve %100 karbondioksit kullanılmıştır. Deney numunelerimiz 2 milim, 250 milim, 250 milim olarak kesilmiş ve 60, 70, 80 santimetre boyunda 3 ayrı ilerleme hızında Almanla birleştirilmiştir. Kullandığımız malzemelerin özellikleri kimyasal ve mekanik olarak SCG 440'ın SG2 kaynak dilimi ve HB205 karışım gazının oranları tablolarda verilmiştir. Çalışmamızda birleştirme işlemi oluşturulan parametreler kaynak makinesine girilerek tam otomatik modda yapılmıştır ve parametreler aşağıdaki tablo değerlerinde gösterilmektedir. Birleştirme işlemi yapılmadan önce test numunelerimizi ortam şartlarına en uygun hale getirerek, temizleyerek birleştirme işlemlerini aşağıdaki standartlara göre çekme testleri, evme testleri, sertlik değerleri standartlara göre yapılmış olup daha sonrasında numuneler üzerindeki sıçrantı miktarları, buharlaşan çinko mesafeleri, makro görüntüleri ve mikro yapıları incelenmiştir. Deney sonuçlarımıza geldiğimizde çekme deney sonuçlarımızda kullanmış olduğumuz 60, 70 ve 80 santimetre bölü dakika hızlarında SG2 dolgu telinde ölçülen maksimum çekme değerleri aslında birbirlerine çok yakındır. HB205 kullanılan karışım gazda 489 megapaskalken %100 karbondioksit gaz ile yapılan çekme değerimiz 487 megapaskal olarak ölçülmüştür. Evme test sonuçlarımıza baktığımızda test sonuçlarımızda ket ve köklerde kaynaklarında herhangi bir kırılma gözlemlenmemiş olup tüm numunelere ait testlerin sonuçları başarılı olarak tamamlanmıştır. Sertlik değerlerini kontrol ettiğimizde her iki deney içinde sertlik sonuçlarımız en yüksek değerleri ıtap bölgesinde, daha sonra birleştirme bölgesinde, en düşük ise ana malzemede olduğu görülmüştür. Itap bölgesi HB205 gaz ile birleştirmelerde 235-245 Hz değerleridir. Karbondioksit ile birleştirmelerde 245-250 Hz değerlerinde olduğu gözlenmiş olup ana malzemeye doğru gidildikçe sertlik değerlerinin düştüğü gözlemlenmiştir. Makro yapılarını incelediğimizde 3 ayrı hızda makro görüntülere baktığımızda burada kısacası HB205'in ısı girdisinin fazla olmasından dolayı malzemedeki erdime daha fazla oluyor. Karbondioksit ise daha az bir erdmeyle daha yüksek hızlarda çalışma imkanı bize sağlıyor. Mikro yapılarını incelediğimizde her iki birleştirme sonucunda ana malzemede sıcaklık tesiriyle tane boyutlarının büyüdüğü görülmektedir. Tane boyutu en yüksek değeri A diye adlandırdığımız dolgu metali bölgesinde olurken birleşmenin gerçekleştiği bölgenin komşu bölgelerinde tane boyutları birbirine yakın olduğu görülmüştür. Kaynak metali en yakın bölgesinde ısı girdisinin etkisiyle taba tanelerini oluşturduğu ve bu kısımlarda en yüksek sertlik değerlerini gözlemlenmiştir. Sen ve İDS analizlerini yaptığımızda yapılan kaynak işlemlerinden sonra numunelerde kaynak bölgelerinde kimyasal analizleri yapıldı ve burada mikro görüntüleri inceledik. Ara yüzeyde demir, bakır, mangan, alüminyum ve silisyum oranlarının tabloda olduğu gibi göstermektedir. Buharlaşan çinko mesafelerini incelediğimizde birleştirme sonrası ıtaptaki galvaniz tabakasının buharlaşması gözlemlendiğini, burada HB205'teki ıtap aralığında 6.33 milim, %100 karbondioksitte ise 5.58 milim olarak ölçülmüştür. HB205 ile yapılan kaynakta buharlaşmanın daha fazla olduğunu tespit ettik. Bizi asıl etkileyen burada bizim de çıkış noktamız olan çalıştığımız proseslerde çok yoğunlukla karşılaştığımız şapak oranları, sıçrantı oranları, kalite problemi yaşatan, kaliteyi etkileyen sıçrantı oranlarına baktığımızda karbondioksit ile yaptığımız çalışmada yaptığımız birleştirmede HB205 gaza oranla %40 civarında daha az şafak olduğunu tespit ettik. Bu da bize kalite anlamında çok güzel geri beslemeler vereceğini tespit ettik. Sonuç olarak birleştirmelerde farklı koruyucu gazların kullanılması mukavemet değerlerini etkilemiş ve her iki koruyucu gazda da ana malzemenin mukavemet değerinden yüksek olduğunu gördük. %100 koruyucu, karbondioksit koruyucu gaz kullanarak yapılan kaynaklı birleştirmelerde sıçrantı miktarı dediğim gibi HB205 koruyucu gaza göre daha az olduğunu tespit ettik. Her iki gaz ile yapılan birleştirmelerdeki parametrelerin incelenip ısı girdileri hesaplandığında çıkan sonuçlara istinaden %100 karbondioksit ile yapılan birleştirmedeki ısı girdileri HB205 karışım ile yapılan birleştirmedeki ısı girdilerinden daha az olduğunu tespit ettik. Her iki birleştirmede sertlik sonuçları analiz edildiğinde en yüksek değerli TAP bölgelerinde, daha sonra birleştirme bölgesinde ve düşükse ana malzemede olduğunu gördük. Birleştirme sonrası ana metal yüzeyinde buharlaşan karbondioksit tabakaları gözlemlenmiş olup TAP'taki buharlaşan çinko miktarları incelendiğinde %100 karbondioksit koruyucu gazla yapılan birleştirmede ana malzemenin yüzeyindeki çinko buharlaşması HB205 gaza göre daha az olduğunu görmüş olduk. Dinlediğiniz için teşekkür ederim.
Teşekkür ederim. Heyecanla karışık biraz. Sorusu olan arkadaşımız varsa sorusu olmazsa. Bunlardan önce.
Teşekkür ederim. Sonucumuz teşekkür ediyoruz. O zaman bu sonuçlara göre karbondioksit formalı gazı karışım gaza göre daha avantajlı olduğunu görüyoruz, doğru mu?
Evet hocam. Şimdi buradaki karbondioksit tabii her birleştirme ve her kalitede için değil, bilhassa galvaniz kaplı çeliklerde ve Prometheus'un geliştirmiş olduğu CNC makinelerinde yapılan denemelerde sonuçlarımız böyle.
Çinko kaybını sadece mikroyapısal değişiklikten genişlik olarak ölçtünüz orada.
Evet.
Elementler analiz aldınız mı?
Yok hocam, sadece görüntü olarak
Almamız gerekir durumlarda. Çünkü gerçekçi bir kayıt var. Ne oldu? Evet, bir bölgesel değişim var ama burada ne kadar bir çinko kaybı var? Bu çinko galvanizin amacını, kaplama amacını, bulunma amacını ortadan kaldıracak mı yoksa muhafaza edecek mi? Bu da değerlendirmelerde bir kriter olacak. Bunun dolayı diğer çalışmalarda onları ölçerseniz daha sağlıklı sonuçlar elde edeceksiniz.
tamam.
Teşekkür ederim.
Ben teşekkür ederim.
Başta soruyor. Bilemem soruyorsun. Sigortaları farklı dediniz. Sigortaları farklı olduğu için sonuçlar farklı oluyor değil mi? Yani,
Evet.
o zaman kontrollü bir deney oluyor mu? Sigortaları farklı. Burada sabit tuttuğumuz şey nedir?
Burada hocam hızları sabit tuttuk. 60, 70 ve 80 santimetre bölü dakikada hızlarını sabit tuttuk.
Isı girdiğimizi değiştiriyor aslında.
Yani ısı girdisini değiştiriyor, evet. Değiştiriyor.
Yani hızlı gittikçe ısı girdimiz düşüyor, yavaş gittikçe ısı girdimiz artmış oluyor.
Evet.
Aslında şeyler hızlı değiştirerek ısı girdisini değiştirmiş oluyor.
Şu şekilde hocam, kaynak makinelerindeki bu özellikleri, yani bu Prometheus'un geliştirdiği özelliği aslında tel hızına bağlı olarak kendi otomatik amper ve volt değerlerini değiştiriyor. Karbondioksitteki etkisi daha düşük tel hızıyla amper değerini düşürdüğü için aynı hızda da olsa, aynı kaynak hızında da olsa daha düşük ısı girdisi sağlıyor bize.
Yani cihazdan kaynaklanan bir şey değil.
Yani cihazın özelliğini kullanıyoruz bu teknoloji.
Yani, evet. Teşekkür ederim.
Ben teşekkür ederim.
Konuşmacımıza teşekkür ediyoruz. Güzel sunusu için. Kendisine katılım belgesini takdir ediyorum. Evet, Cihan Döküloğlu'na çok teşekkür ediyoruz. Bir sonraki konuşmacımız Ufuk Öztürk. Kendisini konuşmasını yapmak üzere davet ediyorum. Kendisi kıdemli kaynak üretim uzmanı, aktif otomotiv çalışmakta. Lisansını makine mühendisliği, Karolinski Üniversitesi makine mühendisliğini tamamlamış. Yüksek lisansı imalat mühendisliğinde şu anda Sakarya Uygulama Bilgiler Üniversitesi'ni yapmaktadır. Sunumu Investigation of Mechanical Properties of SGA ESCGA 440 steel soldered to forehead with cold metal transfer method using different coil wires connected connection areas and junction areas. Thank you. Realizm. Türkçe de pardon. Buyurun.
Tamam mı?
Tamam böyle şey. Böyle diyorsun.
Merhabalar. Ben de önce kendimi tanıtayım. TURKUAZ ben lisans olarak Karadeniz Teknik Üniversitesi Makine Mühendisliği mezunuyum. Yüksek lisans Sakarya Uygulama Bilimler Üniversitesi'nde devam etmekteyim. İmalat mühendisi olarak. Halkpres'te 7 senedir görev almaktayım. Burada üretim uzmanı olarak çalışmaktayım kaynak bölümünde. Yine Cihan Bey'in söylediği gibi bu çalışmada da beraber çalıştık. Burada biz farklı dolgu tellerini kullanarak soğuk mekanik transfer yöntemiyle alın alına belirlenen SCGA çeliklerinin bağlantı bölgelerindeki mekanik özelliklerini inceledik. Bu çalışmada otomotivlerde kullanılan çarpışma kutularını imalatında kullanılan galvaniz kaplı 1.2 kalınlığındaki SCGA 440 çeliklerini birleştirdik. Bunu CNC yöntemiyle yaptık. Bu çalışmada kaynak hızını sabit tuttuk. Burada QC3 ve QL8 dolgu tellerini kullandık. Ve CNC lehimleme birleştirme işlemi yapıldıktan sonra bağlantı bölgelerinde çekme mukavemeti, sertlik değerleri, eğme testleri, buharlaşan çinko miktarları, makro ve mikro testleri yapılarak zincirlerin işlemlerini gerçekleştirdik. Otomotiv sanayisinde kullanılan çarpışma sönümleyiciler için malzeme seçimi başta güvenlik olmak üzere hafiflik, düşük yakıt tüketimi, düşük karbon monoksit salınımı gibi kriterleri kapsamakta. Bu sebepten dolayı mukavemet bakımından güçlü, aynı zamanda istenilen kriterleri sağlayabilen yüksek mukavemetli çeliklere talep çoğalmıştır. Biz SCGA çeliği soğuk katlilenmiş, galvaniz tavlanmış çelikler. Bunlar otomotiv sektöründe mukavemetin yüksek oluşu sebebiyle kullanılmaktadır. Burada aks parçalarında, çarpışma sönümleyicilerde ve güçlendirme parçaları gibi çarpışmaya maruz kalan kısımlarda kullanılmaktadır. SCGA çeliği çift fazlı çelikler. Bu çelikler sünekliği sağlayan ferrit yapı ve mukavemet artırıcı etkisi bulunan martensit yapıdan oluşmaktadır. Cihan Bey'in de söylediği gibi dual part 400
çeliğinin benzer özelliklere sahiptir. TNT birleştirme işlemi bir önceki sunumda da konuşulduğu gibi krom firması tarafından gerçekleştirilmiştir. Düşük ısı girdisi sağlamak ve distorsiyonu engellemek için, sıçrantıyı azaltmak için bu sistemi fabrikamızda kullanmaktayız. Yine sistemimiz ark bazının oluşmasıyla dolgu telinin banyoya daldırılması ve telin geri yönündeki hareketi ve damlacık transferiyle bu sayfada tekrarlanmasıyla süreç gerçekleşir. Bu işlemi saniyede 140 kere tekrarlanmaktadır. Bu çalışmada SCGA çeliği biz kullandık. 1.2 kalınlığında galvaniz kaplı çelik. Birleştirme elemanı olarak Cual 8 ve Cual 3 bakır teller kullandık. Deney numunelerimiz 200 mm olarak sabit hızla alın birleştirme işlemini gerçekleştirdik. Tabloda kullandığımız malzemelerin mekanik ve kimyasal özelliklerini görmektesiniz. SCGA 440, Cual 3 ve Cual 8'in kimyasal ve mekaniksel özellikleri bulunmaktadır. Bu birleştirme işleminde kaynak makinesinde oluşturulan parametre değerlerini aşağıda görmekteyiz. Otomatik bir modda parametrelerimizi sabit tutarak çalıştırdık. Bu birleştirme işlemi yapılmadan önce test numuneleri iki yüzeyde temizlenip birleştirme işlemine uygun şekilde standartlara uygun çekme testleri, eğme testleri, sertlik değerlerini gerçekleştirdik. Birleştirme işlemi sonrasında numunelerdeki buharlaşan çinko miktarlarını, makro görüntüleri ve mikro yapıları inceledik. Çekme deneylerine geldiğimizde Cual 3 ve Cual 8 ile dolgu tellerini kullanarak birleştirme işleminde benzer mukavemet değerlerini yakaladık. Cual 3'te 529 megapascal, Cual 8'de 527 megapascal olarak ölçülmüştür. Eğme test sonuçlarında ket ve kök kaynaklarında herhangi bir kırılma, çatlama gözlenmemiş olup bu numunelere ait testlerin sonuçları başarılı olarak tamamlanmıştır. Sertlik test sonuçlarına geldiğimizde etap bölgesinde, daha sonra birleştirme bölgesinde ve en düşük ise ana malzemede olduğu görülmüştür. Ana malzemeye doğru gidildikçe sertlik değerlerinin düştüğünü gözlemlemiş olduk. Makro yapılarda Cual 3 dolgu teli ile yapılan lehim işlemindeki ısı girdisi Cual 8 lehimleme işlemine göre daha yüksek olduğundan ana metaldeki ergün daha fazla olduğu gözlemlenmiştir. Her iki birleştirme sonucunda da ana malzemede sıcaklık tesiriyle tane boyutlarının büyüdüğünü görmekteyiz. Kaynak metalinin en yakın bölgedeki ısı girdinin etkisiyle kaba tanelerin oluştuğunu ve bu kısımlarda en yüksek sertlik değerlerini gözlemlemiş olduk. Daha sonrasında SEM ve EDS analizlerini gerçekleştirdik. Birleştirmelerdeki kimyasal bileşimler tabloda gösterilmiştir. Birleştirme işlemlerinde demir atomlarının ana malzemeden birleştirme bölgesine difüzyon ile geçişi gözlemlenmiştir. Birleştirme bölgesinde oluşan dendritler açıkça görülmektedir. Buharlaşan ZN mesafelerini incelediğimizde Cual 3'te ıtap aralığı 5.98 mm, Cual 8'de 5.91 mm olarak ölçülmüştür. Cual 3 ile yapılan lehimlemede buharlaşmanın daha fazla olduğunu tespit etmiş olduk. Sonuçlara geldiğimizde birleştirmelerdeki farklı dolgu tellerinin kullanılması mukavemet değerlerini etkilemiş olup benzer mukavemet değerleri ölçülmüştür. Cual 3 ve Cual 8 dolgu telleriyle birleştirilen tüm malzemelerde ana malzemeden difüze olan demir atomlarının birleştirme bölgesine doğru geçerek dendrit yapıları oluşturmuş oluşan bu dendrit yapıların yoğunluğun mukavemeti artırdığı gözlemlenmiştir. CMP lehimlemede ısı girdilerinden kaynaklı her iki birleştirmede de ıtap bölgesinde sertlik yüksek çıkmış, ana malzemeye doğru gidildikçe sertliğin düştüğünü gözlemlemiş olduk. Birleştirme işlemlerinde SCGA 440 çeliği numunelerin ıtap bölgelerinde galvaniz tabakanın buharlaştığını ve Cüzü-3 dolgu teliyle birleştirilen çinko buharlaşmasının fazla olduğunu tespit etmiş olduk. Teşekkür ederim. Hocam biz de yine burada buharlaşan çinko mesafelerini Cihan Bey'le sadece mesafeyi inceledik. Ama birbirimizle dikkat alacağız.
Madem,
Sonra kaçamıyorsun tabii böyle söylüyor.
evet, madem sözüne geldi, o zaman ben birkaç şey daha ilave edeyim. Divizyon da burada. Demirin divizyon olduğu gözlemlediniz. Yani çıplak gözle görmediniz herhalde divizyonu.
Şurada demir atomlarının difüzyonları gözükmekte ve şurada da oluşmaktadır. Yani buradan bu tarafa doğru, malzemeye doğru geçmiş.
Yani biz mikroyatlı atomları göremiyoruz. Değil mi? Yani görebilmemiz için oradan bir elementler ile analiz alırız. Elementler analizdeki demir oranlarının olmaması gereken yerde bir element varsa bu divizyon yoluyla buraya geldi diye yorum yaparız. Yoksa biz mikroyatlıya bakarak demir atomları buraya geldiler, sordular diyemiyoruz. Yani bu devam ediyor. Atomları görüyorum demek gibi bir şey olur. İkincisi, Yakup'un sunumunda mekanik değerler, yanlış hatırlamıyorsam 287 ile 289 megapascal çıkmıştı. Çekme değerleri. Öyle miydi Yakup? Çekme değerleriniz
487, 489.
öyle miydi?
Evet.
Burada 500 küsur çıktı. Gördüm sizler.
529.
550. Yani o zaman lehimlemedeki bu mukavemet artışını neye bağlıyoruz? Malzememiz aynı. Aynı malzemeyi birinde karışım gazın etkisine baktınız. Birisinde de soğuk lehimleme yaptınız.
Burada telleri, dolgu tellerini değiştirdik. Orada koruyucu gazları değiştirmiş olduk.
Yani o birleşme çekme dayanımının bu lehim telleri daha yüksek mukavemet artırıyor, onları kullanalım diyebiliyor musunuz? Diyebilir misiniz? Bu ikisini karşılaştırdığınızda, ayrı ayrı karşılaştırdığınızda tamam bir şey söyleyebiliyoruz da aynı malzeme üzerinde farklı yöntem birleştirme tekniği kullanarak farklı sonuç elde ettiniz ve dolgu tellerini değiştirdiğinizde daha yüksek sonuçlar aldığınızı görüyoruz. O zaman yani bir otomotiv üreticisine o zaman kaynak yerine şu teller, dolgu telleriyle kaynak yapın diyebilir miyiz?
Yani şöyle, Cüzü-3 ve Cüzü-8 otomotiv sektöründe kullanılmakta. Bizim mevcutta kullandığımız SG2 telleri, bu da öğleden sonraki sunumlarımızda yer alacak. Bu dolgu telleriyle birleştirmeleri biz kıyasladık. Bunların bu üç telinde otomotiv sektöründe kullanıldığını biliyorum. Kullanılmakta.
Anlıyorum. Evet, anlıyor işte. Yani bu üç çalışmalarda sonuçları birlikte değerlendirerek bir genel sonuç çıkartmak gerekiyor. Neticede malzememiz aynı malzeme. Birisinde işte karışım gazı değiştiriyoruz. Birisinde SG2 kullanıyoruz. Birisinde de alüminyum dolgu teli kullanıyoruz. Veya bakır silikon dolgu teli kullanıyoruz. Bunların üçünün ortak sonuçlarına göre bir şey söylemek gerekiyor ki anlamlı bir şey olsun. O açıdan bu üç çalışmayı birleştirerek de bir yayın haline getirebilirsiniz. Bunları yaparken de biraz daha söylediğim eksikliklerimizi gidererek, işte difüzyonu örneği söylediğim için elementel analiz almamız gerekiyor. Farklı noktalardan AID'nin ne kadar rahat difüzyon oldu, hangi sıcaklıkta bunlar oldu. Ondan sonra da bir çıkarıp bir öneride sektöre bulunabilirsiniz. Güzel çalışmalar bunlar. Teşekkür ediyoruz. Ama bu eksikliklerde burada işte konferansın amacı bu. Çalışmalarda farklı görüşler ortaya atıyor. Farklı sorular sizlere farklı ışıklar tutan çalışmalarında o amaçla bu organizasyonları yapıyoruz. Katılımın için yapılmış için teşekkür ediyorum.
Evet, ben teşekkür ediyorum. Ağzınıza sağlık. Evet, bu bölümümüzdeki bütün sunumları bitirdik. Evet, sizler. Bu oturumu kapatıyorum. Diğer oturumlarda görüşmek üzere.